So all of our lecture series started with uh, about black body radiations and the four laws that governs it. And what we saw that the black body radiation, if you plot as a function of wavelength, there will be like a curve with a single peak. Okay, and we also notice that this peak depends only on to and the shape and peak, place of the peak depends only on to the temperature and nothing else. So all that matters for the black body radiation is the temperature. We also learned about that why there is a peak and why there is a decrease of the radiation as we reduce the wavelength, and that's because the quantized nature of the energy. If there was no quantization, there was no quantum mechanics, we probably won't be getting the black body radiation, or the black body radiation curve wouldn't look like this. Probably it would have looked like this. Okay, so okay, okay, I will skip. I mean, you remember all that Planck's law, and then from the Planck's law we derived the Stefan-Boltzmann law, Wien's displacement law, and then we also talked about Kirchhoff's law. Okay, so I think we talked more about the absorption spectra, and these absorption spectra are studied something around beginning of the say 19th century, so 1820 onward or so, or 1801 onward. So, and Fraunhofer actually cataloged the absorption spectra into the solar spectrum. And today also many of the line designations that we give A, B, C, D, F lines, they are actually comes from the how the Fraunhofer catalog this line. Okay. So let us say if you had a very good prism and you kind of expand the whole spectrum, what you expect to see is something like a rainbow kind of colors, okay, for the solar radiations. And but if you had a really very good resolutions of the wavelength, what you will see is that some black lines into your images. Okay, and why these black lines are there? I mean, why these absorption lines are there? We call them an absorption line now. Probably that time, at that time they didn't know it when they first observed it. And if you plot this intensity as a function of wavelength, okay, so this is like a wavelength, and the brightness or intensity is the x-axis. So if you plot these things, you will see this kind of a curve that intensity is going on increasing as we come from here to here. Okay, but at the same time, it's not a smooth curve like we observed into the black body radiation. There are kind of kinks into this curve, and this drops, and that is because radiation in this part, say in this part or this part, is not as much as it should be as per the black body radiation laws. Okay, and why this is that also we talked about in last lecture, and that is because of the quantization of the energy levels. So not only the quantization gives you this like a drop from this peak to downward like in black body curve, but it's these small drops that you are seeing, that is also a result of the quantum mechanics, results of the same phenomena. Okay, and we talked about Bohr's model and how that electronics levels are linked. So the fundamental things that you have to remember is that why there is an absorption, because the electrons, for example, they have an energy levels. They can only have certain energy levels. They cannot have any energy that they want to have. So if one energy level to another energy level, like, electron goes, it will go by absorbing the radiation. Then that much radiation will be removed from the radiation, that incident radiations. If it comes down, then this much, that much amount of the radiation will be emitted, and wavelength of that radiation can be given by this delta E equal to h mu equation. Okay, that's the fundamental of everything, I can say. I mean, this is what is a black body radiation. This is what the absorption spectra and everything. What we also studied in last time was these things. So let us say, if you look at this line, for example, if you have been very high resolution spectrometer, that it can only look into only this part of the spectrum, let's say only over the line, then you will see that intensity is not something like suddenly dropping and then again getting back. It's not like a delta function. It has a kind of an smooth decrease and then smooth increase, or if it is an emissions, then it is like a smooth increase and then smooth decrease. So why it is so? That is because we describe the energy levels like a line here, okay, but in reality they are not lines. They have kind of an fuzziness around them. This is like a most probable value of the energy level, but there is a small fuzziness around these numbers, okay, and that is why when the electron goes from this level to say this level, it's not an exact number. It is kind of a probability of range of the numbers, and because of that you get kind of a line shape, okay. And then we also noticed that molecules can have atoms and molecules besides electrons, they can also have different kinds of energies. For example, molecules can be rotating, or they can be kind of vibrating into different modes. And these energy levels are also quantized, so they cannot just vibrate at any energy levels. They can vibrate only energy levels that is given by the laws of quantum mechanics. And when this radiation is incident upon it, let's say it changes its vibrational energy, then they cannot change only any random energy. They can only change from one energy level to another energy level given by the quantum mechanics, and that will give you a corresponding line. So you can have varieties of the lines into the spectrum. And if you look at this line spectrums, for example, this is the kind of a spectrum you will see for the electronics changes in the electronic state of the energy. This is kind of lines you will see when the changes are happening into the rotational energies. This is kind of a spectrum you will see when changes are happening into the vibrational energy levels. Okay. So how does basically the radiation gets this energy? How the radiation and the matter interacts? Okay. So there can be molecules, for example, H2O molecules. They can have a permanent dipole. I hope you are all familiar with an H2O molecule. So let's say it has little positive charge and then little negative charge. So that's kind of it gives it a dipole. Okay. So when there is a radiation passing through it, what is the radiation? So electromagnetic radiation is basically oscillating electric field. So when this electric field changes close to this molecule is trying to, it will try to adjust according to this field that is near to it. Okay. And it will be able to change only if this radiation that is incident that has a sufficient amount of energy to change it from the another energy level which is given by the quantum mechanics. Okay, so it can cause it rotate, it can cause it to vibrate, or like or if it is sufficiently high energy, then it can also change the electronic state. So the spectrum that you will see, if it is happening because of the electronics changes into the energy of the electrons, then it will be mostly in UV and visible. If changes are happening mostly because of the vibrational energies, then it will be like infrared. And if the changes are happening because of the changes in the rotational energy states, then it will be happening into the far infrared. Often vibrational energy levels will not be alone. They will be accompanied by vibrational and rotational together. Okay, they will be kind of uncoupled. So often their spectrum are called vibrational rotational energy spectrums. Okay, so to give an example here, see this green curve. There's an spectrum of water vapor molecules. So water vapor molecule has a freedom to rotate in any directions, vibrate as and in any kind of a way. But this blue curve, for example, is an energy spectrum of the water in a liquid form. Now, when they are in liquid, there are other molecules around it, and they will restrict amount of the vibrations or the rotations they can have. So they can only have certain energy levels. So this spectrum blue curve looks much smoother. Now, water can also be into the ice form, for example, that is shown into the red curve. And in solid form, the restriction is even more stricter, so that becomes even more smoother and so on. Okay, so main point was here. Last time you have to the take home message was this: that line that we are seeing. If you plot this line intensity as a function of wavelength, then you will not have a delta function, but you have kind of a variations that is like smoothly increasing and decreasing. Okay, and these variations are well characterized by the different equations. But there are four regions that these lines, they are not delta function, but they have some certain finite width and height. Uh, One region is that Heisenberg's uncertainty principle. As I told you, that energy levels are not very accurate. They are given by the kind of they are kind of fuzziness around. They are like a probability of the energies. Okay. Then as the energy is radiated, molecule itself is kind of going through a damping. Okay, and that causes the line broadening. Okay, so after emitting the energies, energy levels of the molecules are not the same. Okay, they have little bit changed, and because of that, you get the line broadening. Then, when two molecules collide with each other, their energy levels are temporarily changes. Okay, and because of that, you get a kind of a line shift, and that line shift is known as a Lorentz profile. Okay, and when you are doing radiative transfer calculations for the atmosphere, you have to worry about this part only into the lower atmosphere, because you have a lot of molecules colliding with each other. But if you are studying the atmosphere, say above 50 kilometers, you really don't need to worry about these things, because molecular collisions are not that much. So broadening because of that is not that common. But at higher temperature, at higher temperatures are high, and because of this, molecules are moving in various directions, and they have kind of an velocity distributions. Okay, and when we, as a stationary observer, when we see these moving molecules in different directions, we get kind of a Doppler shift. So instead of getting one wavelength, we are getting kind of a range of wavelengths, which we call it Doppler profile. Okay, and these are given by these equations. You don't have to worry about this equation for time being. This we will probably cover into the advanced lectures. Okay. Okay. Then we also looked at in simple radiative transfer equation. Okay. So let us say a beam of radiation is passing through the material. Okay. Then it will be attenuated, given by this term, and it will be increased, which is given by this term. Okay. Okay. I can take the k lambda common, which is an absorption cross sections rho common, and take it to the other side. The equation will look like this, and this is what the radiative transfer equation in most simplest form. Okay. Now question is that where did we get this first term? This was actually kind of an this is based on the BL-Lambert's law, and it was discovered even before we knew our line absorption spectra. It was discovered before 18th in late 18th century, so before 1801. Okay. And if we have to, so if we ignore this source term, then we can write this radiative transfer equation in this form, and radiative transfer in this form is nothing but the BL-Lambert law. Okay. Now, what are the circumstances that we can ignore this term? So let us say if you are studying the radiation, say let's say solar radiations, for example. Okay. Or you are studying, you have a kind of an beaker full of some liquid or some gas. You pass on the one side you have a lamp, and on the other side you have a detector, and you are studying kind of an absorption into say visible wavelength. Then you can ignore the source term. Why? Because there are no emissions because of the temperature. There are no black body. There are not very significant emissions of the black body that you need to worry about. Similarly, if the scattering is also not much, then you can ignore this term. So let us say if we ignore this term and we find a solution to this equation, this is a differential equation, and if we find the solution of this equation will look like this. Maybe we can substitute, so if there is a small distance into a material, then we can assume that its absorption cross section is same along the path. So you can write it outside, then you integrate the density over length. And if you integrate the density over the length, what it will be? It will be called the path length. Okay. So you have studied. I mean, we have talked about Beer-Lambert law. So last lecture I mentioned to you that how the Bouguer was drinking the wine and he discovered this law, but it was the Beer and Lambert. They give this law a mathematical form, which is this form. Okay. So they kind of given you kind of a language to speak about this law. If you look at this law, what does basically it says? So U is what? U is a density multiplied by the length traveled by the radiations. Okay, and radiations. So absorption cross section is fixed. Then it will only depend on to this density multiplied by. So if you have density changing and you're traveling, then this is not anymore constant. Okay. Okay. Okay, so this is so what is the radiative transfer study? Okay, so radiative transfer is basically study of the energy in form of the radiations, and then this is the equation of the radiative transfer. So you start with these equations, and then in different circumstances you can find out the solution of this equation. Okay, so for example, we have taken a very simple case that let us ignore. There is no let's say there's no scattering or emissions, black body emissions, then you have only these terms, and solution to this was given by this equation. Okay, and this is also a statement of the Beer-Lambert. So either you can represent the Beer-Lambert law in this form, or you can represent the Beer-Lambert law into this form. Just give me 1 minute. Huh? I need to drink the water, so just hold on, just 2 minutes. Yep. Okay, I'm dead. So we are talking about the radiative transfer equations, and it's one of the simplest solutions is basically the Beer-Lambert law. And the Beer-Lambert law is something that there has many applications. Actually, all of the instruments that you see in atmospheric sciences, they are basically based on to the Beer-Lambert law. Okay. We study the stars. I mean, astronomy is kind of, you can't do astronomy without Beer-Lambert law. You can't do chemistry. I mean, if you are using the optical instruments to measure these various solutions, then in other fields also, there are many applications. I will come to that to an example of that. Okay. So let us say if we write this Beer-Lambert law in this form, okay. So this term shows the change into the intensity as a function of the distance traveled. Okay. This term K is absorption cross sections, rho is in density. Now be careful with density. This is not the density same as so for example, if you have a glass full of water and you are passing a beam through this glass full of water, then the density rho represented here is the density of the water. But if you have a say cloud, okay, which has a cloud droplets, then this density is not the same thing, okay. then it is the number of the so what is important for us is not the really a density, but the molecule. I mean, what do you think that why the radiation interacts with the molecules? Not because the molecule has a weight, okay, or mass. It interacts with it because it is a molecule. It has an electronic structure, and the electromagnetic radiations are the kind of an uh, moving electric field. So they can interact with each other. Okay, so what is important is the molecule, not the mass of the molecule. But when you are representing in this form, what you are talking about the mass, because when first Beer-Lambert law was discovered, its application was mostly to measure the concentration of the various species into the say water or in liquid or in air and so on. Okay, so this term became very this thing, but this term is not very convenient if you are talking about say extinction by the aerosol particles. Okay, so instead of these things, K in terms of the mass cross sections, really truly physical term is the simply cross section of the molecule. Okay, and if you have a cross section, extinction cross section of a molecule, we can multiply it with number of the molecules. Okay, and then what we get is the Beer-Lambert law, and that is the form of the Beer-Lambert law. That's the real form of the Beer-Lambert law. This is also a Beer-Lambert. So suppose you are dealing with a gas, okay? So all the suppose you are talking about CO2 gas, all the CO2 molecules are the same. It's not like one CO2 molecule is having a different absorption cross section or extinction cross sections, and another CO2 molecule has a different cross. They are all same. So as long as you can find out the density or concentration of the CO2, you can simply use this easily. But if you are talking about say particles, aerosol particles will have different chemical properties, different sizes, and even different optical properties. So in this case, this equation will be of no use. But these equations, yes, this equation you can use into the for every kind of. This is like a general equation. This is a specific equation for the gases. So let's say if you have this kind of an equation, uh, or maybe this kind of equation, one thing you have to remember is that extinction is what is a loss of the light, and what are the processes that causes the loss of the light? So there are two processes that we can lose the light from the beam. One is because of the scattering, original energy, incident radiations is scattered away into the different directions. So in the original directions of the beam propagation, we have a loss. Okay. Another is the absorption. Okay. And do you have an idea why there is an absorption escape? I mean, if you had to kind of do calculations of the absorption or scattering, what is that property you will require to know? Anybody? Anyone knows that if you want to calculate the scattering or absorption of a molecule, what is that? What is that fundamental property of the molecule or species that is actually used to do the calculation of the scattering and absorption? Do you have any kind of, can you guess it? I mean, I'm sure we have not talked about it. I have not taught you. And I guess you may not have even been taught, because you might have been taught about the absorption, but not about the scattering so far. Yes, Pooja, you were saying something.
Sir, I think we have differential scattering cross section.
Sorry, I was not able to hear your answer. But anyway, so let me give you the answer. The scattering or absorption, if you want to do an scattering or absorption cross section calculations, you will need refractive index of the particle or refractive index of the material. Okay, and refractive index is a two part. One is called real part, one is called imaginary part. The real part of the refractive index gives you scattering, an imaginary part of the refractive index gives you absorption. Okay. So if you have if you know scattering and absorption of a molecule, you can calculate the extinction cross section simply by taking the sum of them. I mean, that is a good news for us. I mean, we can now talk about the scattering and absorption separately. We don't really need to worry them together. Okay, it's not like you have to every time calculate. If you wanted to calculate extinction coefficient or extinction cross sections, you don't have to worry about absorption and scattering separately together. Okay, if you know the scattering, you can proceed with it. If you know the absorption, you can proceed with it. Okay. Uh, Now, this part actually that there are some of, I mean, the scattering extinction cross section is a sum of scattering and absorption cross section was kind of a counterintuitive. Why counterintuitive? So, how did I view when I material and radiation beam interaction? So, let us say if you have a beam of radiation going and if you have a kind of a marble in between, okay, so marble will kind of obstruct certain part of the beam because of its size, okay, and the rest of the beam will keep on progressing. So the part of the beam it can obstruct will be equivalent to the cross section of the part. Let us say the beam marble is not allowing any radiations to pass through within it, okay. So this is kind of an idea I had about cross section. So if you have a cross section, it's like a particle, like a spherical particle blocking the beam. Okay, and what you are having is that shadow of the particle and the remaining part of the beam. Okay, so that's why the beam depends on to the cross section. Okay, beam intensity when after passing the marble, the intensity depends on to the cross section because it obstructs the certain part of the beam. But let us say it has an absorption and it has an scattering. How can it can be an additive? That was the kind of an I mean, I was much troubled by this idea that how can there be an additive? If suppose you have absorbed away all the radiations, there is nothing left to do with scattering, or you have a scattering, where is the question of absorption? Okay, but anyway, science doesn't work as per our intuition. It works as per its own laws. And good news for us is that they are kind of there. You can do the sum. I mean, if it was a multiplication, our life would have been much difficult. But luckily, it is kind of when you can do the sum. Okay. Now, in atmospheric sciences and even in astronomy and everywhere, this absorption cross section is not very convenient term. Okay, it you have to if you have an absorption cross section, you still need to know the concentration and so on. So if you are interested in concentration, finding out the concentration of the species, then knowing the scattering cross section has a meaning. If you are interested into the change in energy, then this term is kind of a burden onto us. This n is burden onto us. So what we can do is that we can combine these two terms. Okay. So k multiplied by n, we call it an extinction coefficient. And can you tell me what will be the unit of the extinction coefficient? You can write down into the comment box, or you can just raise the hand and answer it. Yes. Yes, please. Anybody? What would be the units of the extinction coefficient? That's my question.
Sir, we give it as per concentration per meter. If we have any 1 meter length, then
Say it again. Per.
concentration inverse meter inverse.
Okay. You are close, but that's not the correct answer. Anyone else wants to try? What is the unit of the cross section? What is the unit of K here and what is the unit of the K here? In fact, I had shown it into the previous slide. I want to find out whether you people were really watching at the slide or sleeping. Please give me some answer. I mean, it's not that difficult questions I have asked. So,
Per meter?
which one you are giving? Answer. Your answer is for which question? For the cross section or for the coefficient?
Sir, it's for cross section. Cross section.
Cross section for the cross section per meter answer is a wrong answer.
Sir, for cross section meter square.
Hmm?
Sir, for cross section meter square is the unit.
Okay. Meter square is a unit for this K lambda prime here in this equation. Cross section is in the meter square or centimeter square per molecule. Okay. Per one molecule. Okay. But what will be the unit for this one? Hmm?
Sir, sir, B lambda, beta lambda.
I'm talking about this. I'm talking. Can you see my cursor into? Sorry, let me put the slide. Ah. This is the okay. This is the term. You have given answer correctly. That unit of this term is centimeter square per molecule. This is the term I am asking. This is I have actually shown the value for this term in previous slide. Let me show you my previous slide. Here is that number given here. Can you see that? Can you read this?
Yes, sir, centimeter square per gram.
Gram. Okay. So if you give the extinction coefficient defined like this, it has a unit of per meter. Okay. Because this is a centimeter per molecule, and then you multiply by number of molecules. Okay. So this n is what? So n is the number of molecules per centimeter cube or per meter cube. Okay. Number density basically. So if you're giving a k into this term, centimeter square per gram, and if you give the rho in terms of the gram per meter cube or gram per centimeter cube, you will get a term beta that is the same. That is the same unit per meter inverse. So by doing this exercise, by replacing this term, k into n or k into rho, we are getting a new term, and that term is defined as an extinction coefficient, and it will have a unit same. You don't have to anymore worry about the what was the unit of the k. I mean, suddenly, if somebody has given you a unit of the cross section value, you have to ask the cross section value. Whether it was for the weight or whether it was for the volume or whether it was for the number of molecules per molecules. Okay, but once you have a beta, you don't have to worry about that part. You know that it is always per meter, okay, or per kilometer, whatever this is. But it doesn't. You don't have to worry about whether it was a molecule or whether it was a weight of the mass of the molecule. Okay. Uh, okay. So how do we measure the extinction coefficient is another question. And extinction coefficient has a many utility. As I mentioned, if you want to find out the concentration or this is basically you find out the extinction coefficient, and from that extinction coefficient you calculate the concentration. Okay, because K always remains the same for the molecule. It doesn't really change from molecule to molecule. So only concentration changes, whether it's number concentration or the mass concentration, and that will give you a change. So this is what you can actually measure into optical instruments, and from that you can actually derive it. So there is another application of it is into terms of the visibility. Okay. Uh, So what is the visibility? So visibility is the distance that you can see into the atmosphere. Okay, how far you can see an object distantly. For example, you can see this mountain very clearly. Then this mountain looks little fuzzy. Then there are another mountain range that's still kind of an fuzzy, and there may be a mountain behind this also, but we can't see it. We can't really distinguish it from the air. Okay. Uh, so let us say you wanted to find out the visibility. Why you need to find out the visibility? Okay. Uh, so if you are an say aeroplane pilot, you need visibility. Even if you are kind of driving a car or something, you need to have a reasonably good visibility. Then only you will be safe. For example, why there are more accidents during the fog? Okay, because during the fog, visibility is reduced. Okay, even though like in the it is like daytime, but you can't see a very long distance. Okay, so visibility is very what is called life. Knowing visibility is something that your life depends on to it. Okay, so in wonder what circumstances we can actually distinguish the visibility from the sorry, one object from the background. Let us say there is an atmosphere only, and there is an object into it. Let's say dark color object into it. Uh, what does it allows you to distinguish it from the background? Okay, it's a contrast. If there is a contrast with respect to background, then you can distinguish that object from the different. For example, this red dot here you are seeing, because there is a contrast into the red dot and the surrounding image, you are able to see it. Here you are able to see it much better way because contrast is more here, contrast is less here, for example. So it will not look as bright as this one. Okay, so how do you measure the visibility? Okay, how many of you ever visited the airport? Just raise the hand, and maybe Tejas or somebody can calculate how many people have visited the. Okay, Dhyani, hers. Anyway, so why I want to make a point is that at some point of life you are going to visit the airport, and when you will visit the airport, you will see there is always one tower close to the airport, close to the runway. Okay, and the tower has a kind of an all side is with glass windows. Okay, and there one guy will be sitting, and his job is to look around, and he will see a long distance objects. For example, say somebody is in Ahmedabad airport ground staff, he will see, and if he is able to see say Patang hotel, or he is able to see some big known building, so he will say that okay, I'm able to see this long distance, and the Patang hotel is so much kilometers from the airport. So today's visibility is this thing. If he is unable to see the visibility, unable to see that landmark, he will say that okay, visibility is less than the 2 kilometer, or less than the 1 kilometer, or less than the 10 kilometer, and so on. So if you see the visibility way people used to measure, that was not very objective. Okay, so this was a problem, particularly during the Second World War. Second World War, if you are following the history, you will know that Second World War was the time when aircrafts were used very extensively. Okay, and this when these pilots, when they are approaching the runway, they need this information that how far they will be able to see the runway. Okay, if they are very close and unable to see the runway, it means they are trying to land somewhere else. I mean, you will not know exactly that where you are landing until you are really able to see the runway with your own eyes, and then you want to find out that if you are really coming down very fast, you know, and you need to know from very long distance that where the runway is. Okay, so they devised one instrument. They wanted to make it very objective. They don't want to depend on to the people. Suppose there is a mountain. Suddenly, after a few months, you set up a new runway at some different places because this is a war going on everywhere, and you want to kind of have a runways, temporary runways, and so on. Or you have new staff. He doesn't know how far is that particular landmark from the runway. So they wanted to do this objectively. So they devised an instrument called nephelometer. And there is one nephelometer available into the St. Jewish College. Maybe Tejas, are you there? Okay, he may not be listening this lecture. Probably he just log in. Anyway, St. Jewish also has a nephelometer. Physical History Laboratory also has a nephelometer. This is a device. Okay, this device measures something that actually the nephelometer doesn't measure the visibility, but it measures something that can be used to calculate the visibility. So, what does the nephelometer measures? Anybody has ever visited St. James College, this lab? Have you seen the device called nephelometer there? Nephelometer.
Yes, sir.
Okay. So, if you have seen this device, what does it measure? Do you know that?
Sir, it measures forward scattering and backward scattering. So from that, we can calculate many parameters like number density, and it can be used in single scattering albedo.
Okay, good answer. But first of all, it doesn't measure the forward scattering. It measures the total scattering and backward scattering. If you subtract the backward scattering, you can get the forward scattering from that number. Okay. Another thing is that scattering is not the something quantitative. It is a kind of a phenomena that it looks into the phenomena of scattering. But what does it quantitatively measures? What that number that displayed when they are displayed onto the screen? What is that number? What is the unit of that number? If you pay attention, it measures the scattering coefficient. Okay, which we talked about in this equation previously. It measures the scattering coefficient. So this is an extinction coefficient, and I mentioned that cross section is a sum of scattering and absorption cross section. Similarly, extinction coefficient is also sum of scattering coefficient and absorption coefficient. If you follow from this equation, you can know that you can take out the n common. I mean, if you substitute the k into this equation, and then you take out the n, you will know that basically extinction coefficient is the sum of these two, scattering cross section, scattering coefficient and absorption coefficient. Okay, and what nephelometer gives you is the scattering coefficient. Okay, so it measures the scattering coefficient. Okay, let us for time being we assume that there is no absorption. They are very purely scattering kind of particles. There is absolutely no absorption. Then your extinction coefficient is same as a scattering coefficient. Okay, beta. Now you have beta, and you want to tell the pilot that my beta is this much. He will not understand anything. He wants a number in kilometer. How many kilometer away I will be able to see my runway? That's what he wants. So he wants to see a number that 2 kilometer or 3 kilometer, not that 0.5 10 to the power minus 4 or something like that. You don't want to do the calculations when he's kind of driving the aeroplane. Okay. So our task is to convert extinction coefficient into the visibility. And how can you do that? Okay. So what makes you see the object is the contrast. Okay. And how the contrast is calculated. Okay. So let us say B0 is an background brightness, and B is brightness of an object that you want to see. Then contrast is basically the ratio of B minus B0 divided by B0. Basically, the percentage difference into their percentage difference into the brightness with respect to the background. So again, my question is, what is the brightness? I'm not sure whether I mentioned you this in my first lecture or not, but in first lectures we have covered many quantities. Okay, one of this quantity was the radiance, and another name of the radiance is intensity. Okay, and brightness is a synonym of the intensity. So brightness is same thing as an intensity. It is same thing as a radiance. Okay, and all these laws that you are talking about, this is an You can call it intensity, or you can call it a brightness, or you can call it radiance. Okay, they are same thing. Okay, so all these laws are for the radiance. That's why we paid so much attention to this definition into the first lecture. Okay, so B, so you know the laws that are governing to the B. Okay, and from that you can calculate the C. So if the value of C is greater than 0.02, that is at least there is a 2% contrast, then only you will be able to see the object separately from the background. That is the limitation of the human eye. Okay. So let us kind of find out. So if you have an extinction coefficient, okay, and you can calculate the distance that where your contrast will reduce to the 2%, that is the distance that pilot will be able to see the runway. So let us do that, okay? And how do we do it? Okay, so this is again the nothing but the simple form of the radiative transfer equation. Okay, what you are talking about, the change in brightness as a function of distance. Okay, here I have written C is a contrast, and I have written and we want to tell. I want to tell you that C is a function of the distance. B is a brightness of an object. Okay, and it's also a function of the distance. B0 is a background. Okay. My question is whether the B0 will be function of distance or not to you. I have written them as a function of the distance, but what do you think? Any answer? Anyone want to want to do a guesswork onto this?
Hello.
Yeah, hey.
Sir, if we are very far from our source, from where we are getting light, then at that point we can say that our B0 is not depending on us. But if we are near to our source from where we are getting light, then we can say that it depends on distance, how much far from we are from our source. Probably, sir.
Very good. Good answer. So we are talking about in a situation. Let us say you have an atmosphere and you have kind of say black object. Okay. So when it is very close to you, let's say S is 0. Okay. You are not getting any kind of an. You have kind of you can see very distinctly this object, but background is an atmosphere, and ideally the background. That's why we call it a background, that it doesn't change as a function of the distance. Okay. So even though I mentioned this as a function of distance, but it's really not changing with the distance. That's the idea. Okay. So as I mentioned these things, this is an equation, radiative transfer equation. So this is a loss term. Okay. So if it is in brightness, or it can be a kind of an, you say, uh, so let's say if you had in a kind of an here we are talking about the black object, and as we are moving away, okay, there is no actually radiation coming from the object, but we can also talk in different way. Let's say we had a lamp and we are taking this lamp away, okay, then the decrease in the intensity or decrease in the brightness will be given by the Beer-Lambert law. This is the equation for it, and there will be an increase into the this is that increase, that whatever that background radiation is coming, that is not directly coming into it because there is an object between us, but they can be scattered into our directions through a multiple scattering, and that I represent by the beta prime. Okay, here. So this is a kind of a source term, this is a loss term, and this is how the radiation will change. Okay, I've already mentioned these things. Okay. Now, if you do kind of an same thing for the background radiation or background object, uh, you can write this equation like this, because source of the scattering is only background. Your source object is not the source of the scattering. So from the background radiations you have scattered. So this term remains same. This term is loss term for the background, and this has to be equal to 0. That's the very kind of a definition of the background. Okay, otherwise it won't be called the background. Okay, so if you equate this to 0, then you know that beta lambda is basically beta. So this beta prime and beta both are same thing. Okay, you can have only that much scattering into your direction as much the loss of the scattering from your direction. Okay, so if you put these terms into this equation, you will get this is the equation. Okay, so if you substitute this, so what basically you have to do is that you want to find out C as a, so how the C changes as a function of the distance. So you do the differentiation of the CS, then you will have the differentiation of these two terms divided by this term. And if you substitute all of this information we just now discussed, you will get this equation. Okay. And this is the equation. This is basically the radiative transfer solutions that we discussed into the previous slide. Okay. So sorry, there is a small mistake here. You have to have kind of an CS0 here, okay? And it's not really a mistake, but I've forgotten to mention about this thing. So this will be so this CS, like, just let me go, okay? In this case, for example, I lambda is I lambda at the 0th distance, then this exponential term, okay? Similarly, CS, if you take the CS from this equation, you do the exercise, you will have a C at a 0th distance, but you have 100% contrast. Okay, that's what kind of you define your problem, that I have full contrast if the object is close to my eye. Okay, so this number is CS at 1 is 1. So I substituted 1, and then you have exponential this term. Now, do you remember what was the number I told you that you need to have CS? You need to have contrast in order to be able to see it. How many of you remember that? Just shown in previous slide only. What should be the amount of the contrast?
0.2.
Not 0.2. But you are not very far away though.
0.02.
Yeah, correct. 0.02, 2%. Okay, so 0.02. Okay, so you know the 0.02 should be here. So to get the 0.02, what should be the S? That is our question. That is what the person sitting into the tower, person who is handling the nephelometer wants to know. Okay, that in terms of the S, and this value you substitute 0.02, then what will be the value of S? I want you to calculate and tell me. It's not very difficult. You can do that. What are you going to do? Anybody wants to tell me? I mean, this is the problem. How you are going to proceed?
So can you repeat the question, please?
See, in order to see an object from very, very long distance, you should have minimum C, value of the minimum C is 0.02, okay? So to get the value of 0.02, what should be the value of S? What is the value of S that will give you C, value of C 0.02? That's my question. For what value of S you will have a contrast 0.02 from this equation?
But sir, we have the value of beta lambda.
Sorry.
So we don't have the value of beta lambda.
Yeah, yeah. So in terms of beta, what will be the value? Keep the beta.
3.91 by beta.
Yeah, that's correct answer actually. Yeah, Chintan also has a given correct answer. Okay. So you have now you have now the visibility. So S is what? S is your visibility. That is the distance that you will be able to see. Maximum distance that you will be able to see. And that distance is given by 3.91 divided by B lambda. Okay, or beta lambda, sorry. So what is the value of beta lambda? Anybody knows the value of beta lambda for the St. James College atmosphere? If you had an atmosphere similar to the St. James College, I mean, any of you are going to college, or you are all of your lectures are the online?
So online lecture.
Okay, so you have not got the
Actually,
opportunity to really go and see the instrument and read the value.
So some of the students are there in the laboratory. They are
Okay.
working with
Yeah.
the
So
instrument.
Tejas, I want one number. Let's say what was the yesterday's scattering coefficient values for say 500 nanometer or some visible wavelength.
Sir, it is around on an average it is around 30 something 30
See,
35. It varies.
35 watt. Actually, if you see the screen, you will have three values. One will be the relay, one will be the total, or one will be the aerosol.
Sir, actually the currently the instrument which we have, it doesn't have screen. It we have to download the data
Mm-hmm.
after every day at night. So it doesn't have the display screen on it.
Mm-hmm.
But the accelerometer do have, but the accelerometer only shows the black carbon concentration on it.
It will give the black carbon concentration. So, any of the number you remember or no?
Currently, sir, the black carbon value is around 7 nanogram per meter cube.
Uh,
But yesterday reading for scatter means total scatter, not for back scattering is around 35 overall average, sir.
okay.
Scattering coefficient.
Okay. Let me just see my whole. I have some old files. Give me one moment
Yes.
to see. I just want to see. I want to use some real numbers, not the numbers, imaginary numbers. So let me see.
Sir, I have one data.
And who is this?
Sir, Heath.
Yeah. Yeah. Tell me.
Hello, sir.
Yeah. Tell me. Can you hear me?
Yes, sir. Yes, sir. Sir, I have a data. Uh, Sir, I can say total scattering for red, green, and blue. Three wavelength, different.
Mm-hmm.
Around till now, I didn't taken average, but around I can say that it's 213.75 scattering coefficient.
So repeat it. 1.
213.75. But it varies, so I have to take average for whole day, and then I can say the average number.
No, it's all right. Let us say if it is 213.75 now, what is the unit of that number?
Sir, it is probably per meter.
Per meter.
Yes, sir. But
Uh,
I am not sure about it, so I have to see. I have.
so if you divide by 1,000, okay, it may not. I mean, number looks very close. 0.213. Yeah, if you divide by 1,000, then it would be. No, I think no number looks very high actually. There should be 10 to the power something in that number.
Yes, sir.
I'm just trying to get some old numbers from my. Well, I have not brought my office computer here, so hmm. Can anybody is there in the lab? You can just call and find it out. What is the number? I mean, that is the point
So
one.
just a minute, sir.
Sir, I have
Yeah.
sir, it's in meter inverse. In manual, they are showing that the data is in meter inverse.
Okay.
But
Sorry, I couldn't get your full answer. But my question is the 213.75 10 to the power minus 5 or something like that should be there. Minus 6 may be there. Million meter maybe. So I think there may be 10 to the power minus 6. That's what my that's
Yes,
kind
sir. It
of
is
my.
micrometer.
Hmm?
Micrometer. Yeah, it is 10 raised to power minus 6, sir.
Yeah. So 213.75 10 to the power minus 6 per meter. That's the number you are having in Ahmedabad. And reasonably good residential area, I would call. Okay. And now you have the equation for the visibility. Can you do the calculation? What would be the value of S in terms of kilometers? Let us say your friend is kind of trying to land. He wants to do an emergency landing in grounds of the St. Joseph's College. He may be having parachute or something. So you want to see whether how far he will be able to see the St. Joseph's College from the sky. And your task is to give him a correct estimate of the visibility. Everybody should calculate S or visibility and tell me. Mujara. quick. I mean, we don't have some whole day here available. I'm also trying to do that calculation. Just now we have got this equation. I think at least two of you have solved that equation correctly.
Sir,
Yes.
around 15 to 20 kilometers. 15 to 20 kilometers.
15 to 20 kilometers. Okay, how many have got this answer? Let me also do the calculations parallelly with you. Okay, so I have. Okay, how many have got the same answer or at least close by answer? So I think that originally that number 213, they may not have these things.
सर बीटा का एग्जैक्ट वैल्यू क्या लेना है 213.77 या क्या?
Yes, 213.75 per meter. I think that 10 to the power minus 6 should not be there. Yeah, so originally whatever that he has given that number is correct per meter, 213. Because otherwise you will get very, no, sorry, it should be there. I myself is confused. Anybody else is getting the answer?
So 16.9
Okay, so around
kilometer.
16 to 15 kilometers you are getting that answer. Okay. What I wanted to do is that one more calculations. I mean, you may have this number. I don't know. Is this number the total or is this the relay? But if you have access to the nephelometer data, they will have the value of the relay, and they will. Okay, somebody has answered. Okay, Heath has answered. Hers has answered. Dhyani has also answered. Okay, so like a lot of you have got it correct answer. Good. What I wanted to do is that, let us say you did not have any pollution into the atmosphere, then there will be only the Rayleigh scattering into the atmosphere, okay? Only the scattering by the air molecules. And that number is also given into the nephelometer along with the total scattering coefficient. And if you put that number, you will get a visibility number. That number is your maximum visibility, even when there is no pollution into the atmosphere, how far you can see into the atmosphere. Okay. And I wanted to find out that answer. So what I want, Tejas, can you hear me?
Yes, sir.
Okay. So what you can do is that you can provide this. They should get this scattering coefficient for the air molecule only without pollution. Okay.
Okay.
And for the different pressure values, and they
Yes,
should
sir.
calculate. Let us say. One can do a calculation at the sea level, one can do the calculation at the say 1 kilometer of altitude and so on, and find out what would be the visibility.
Okay, sir.
Okay, just as an assignment. Anyway, let's go back to our slides. Okay, so what is the time now? Okay, we have still time. Okay, so again and again the same. Now, as long as this lecture series will go, probably you will keep on seeing this kind of an radiative transfer equation. This equation, in earlier calculations, we ignore this J, okay? And then we got this Beer-Lambert's law. Then we also kind of included the J, but we really did not include the J. We included only the scattering component, and we got the visibility number. We use these equations to find out the visibility, okay? And now we know that how to help the pilots, okay? But you can have the J, that is a radiation, from the black body, that's from the Planck's function, okay? B. Let us say you can have in a situation where there is not much scattering, okay? Atmosphere is very thin, but there are temperatures and there are radiations coming from the, because of that, okay? So you can have the scattering 0, but radiation from the temperature of black body radiations can be there, and that will be given by this equation, okay? Now, if you are paying very close attention to these things, you should have a question at this point. When I say that I can write this equation, it's not really straightforward. There is something, जैसे वो जादूगर होता है ना, हाथ की सफाई. So in this equation, there is an हाथ की सफाई. What is that हाथ की सफाई in this equation? There is something I did, okay, that allowed me to write J. I mean, there is something we know, but I did not mention, that allowed simply put J instead of B. I mean, if you know, when I did this here, okay, I did not just simply put it, okay. If you see in this case, we are not taken this common and taken to the other side, okay. Original equation, so go back to this original equation, okay. So this is an equation. You see, I writing K here, but when this came, when we did this exercise, I did not write this into the other side. I kept it onto this side. And then I have shown you that I can actually tell that this and this are same, okay? The same exercise I have not done it here. I have simply written it here and simply written these things. What laws allows us to do that? Okay. Why we can kind of take the K common. Okay. What was the J? Okay. J was a small j divided by the K. So what does it allowed us? Small j divided by K replaced by the B lambda or the Planck's function. Okay. I mean, you can think about it, but what allowed us this was the Kirchhoff's law. Okay. Whatever is emission efficiency, if there is an absorption happening, and that is given by this term. Originally, if I wanted to be very honest, what I would have done, that I would have kept the K here, K lambda rho here, K lambda rho here, okay, and then take the K common, okay, and but what does it allow this K to the common, take the common was that, so if there is an absorption is happening with certain efficiency, say K, that is absorption cross section. Okay, so now we have good answer, 200. Okay, so Heath has put one answer into the comment to our previous questions. What was the okay? Heath has given some answer to the visibility and number for the scattering coefficient. Okay, and that number is, I hope that number is correct, 10 to the power -2 or something. Okay. And if you do that number, you are getting very small visibility. Okay. Anyway, I think we need to look into it. I think Tejas, you can say, I don't know, you're listening, huh? So you can share some data. Maybe you share 1 day of data, they take the average of that days of the data. and then they can do the.
Sure, sir. Sure, sir.
Okay. Anyway, so let me coming back to this slide. Okay, so what does allowed me to do this thing was that if absorption is happening with an efficiency say k lambda, then emission will also happen with the same efficiency of k lambda, and that is the Kirchhoff's law. Okay, so here when we been able to write like this in this equation, it's because of the Kirchhoff's law. Okay, now you might have noticed that this k lambda into rho is troubling us a lot. I mean, it's remaining there. I mean, we can replace it with beta, but then still we have to worry about the ds. Okay, so we can have actually one more quantity. We can call it an optical thickness. Okay, and that can replace all of this denominator. Okay, so let us define the optical thickness as an integration from s to s1 k lambda rho into ds prime. Okay, now so I think heat is already working on aerosol optical depth and projects like that. So there is a difference between optical thickness and optical depth. They are similar quantities, but they are not the same quantity. Okay, I will come to that difference in later slides, but don't confuse this thickness with the depth. Okay, that's only you should be careful with the nomenclature because it looks like into the atmospheric radiative transfer, people have run out of the symbols. So this K symbol you will see for varieties of the regions, tau symbol you will see for the varieties of the different quantities. So every time when you look at the equation, remind yourself that is it the same quantity that we have talked earlier or is it the new thing we already defining. So anyway, so if we write integration, so let's say your beam is traveling in this direction and this is s to s1 distance. Okay, then you can do this, you define this integration, that quantity you call it optical thickness. Okay, and if you do the differentiation of this quantity, that is d tau, sorry, here I have made small mistake, it should be negative sign here. Okay, okay, here it is correctly defined. So if I write a d tau in this terminology, it should look like this. Okay, yes, so once we have this quantity, we can write this equation even much simpler form. Okay, we can write this equation into this form. Okay, now you don't have to worry really about the this distance. Why we wanted to get the read of the ds. Okay, so as we go into the atmosphere, or I mean, you do the astronomy or those kind of calculations, you are really not worried about the physical distance that is being traveled, because what you are worried is that for a certain distance, if the radiation is decreased, okay, you can do these calculations and then you can find out the distance, physical distance separately. Okay, so in a way, this terminology allows you to write equation in a form that is not really dependent onto the like coordinate system. I mean, as long as you are doing all your calculations into this term, in this kind of an equation using the tau, you really don't need to worry whether you are using the Cartesian coordinates or it's a spherical geometry, or so you. It allows you to do the calculation without worrying about the geometry of the problem. Okay, that's the reason we want to kind of have the tau here. Okay. Now my question is here to you. So if I define the tau in this manner, what is the unit of tau or optical thickness? At least I should get three answers. I mean, at least three people, three students should reply this. At least I know that at least minimum three people are listening to my talk. Have you got my question? Are you able to hear me? I mean, sometimes I'm not sure really if my microphone is working or not.
Yes, sir, it
So,
is audible.
okay.
Sir, meter cube.
Meter cube is not the correct answer. Heath may be knowing because he had sent one question a few days back regarding optical left. So probably he might have worked and he know. But if you look at this equation, you can do it calculations straightforwardly. I mean, all of the quantity you know. What is the K? What is the rho?
Sir, rho is density.
Yes.
So meter raised to
Rho
4
is
is
actually concentration in this term. I mean, in some loose sense, it's density, but correct terminology is a concentration. Yes, please. Anybody, raise your hand. I mean, if you're not understood the question, then raise your hand. Otherwise, I will assume that all of you have understood the question and doing the calculations. I mean, it should not take this much time. I mean, it's not like you really need to use a calculator or computer to get the answer to this question.
Actually, sir, while we are working on thickness, sir, we are taking exponent of it. So not here, but in our calculation. So, sir, we are getting unit less.
Sorry, I couldn't hear your voice was in between breaking. So you gave some answer, but I couldn't hear it.
Hello,
Yeah, tell me.
sir. When we are doing in our lab, uh, we are taking exponent of it. So we are getting a unitless number. But here, if we see this equation, then we only can say that it's per meter cube from this equation. But when we are doing that in sun photometer with sun photometer, it's taking exponent. So we are getting unitless number.
Okay, so you are getting the
sir.
unitless and some other place. That is the correct answer. The unit, this should be the unitless. Even though it's called thickness, it is unitless. And here also you should get the unitless. That's the point. I mean, this is the same quantity as what you are using in the exponential terms. Okay, so you should get the unitless. Yes, Pooja, you were saying something.
Sir, I got gram or kilogram.
Gram per kilogram. Okay, so gram, let us say you can put 10 to the power minus 3 and you can always cancel out the gram per kilogram.
No, sir, gram or kilogram.
No, that is not the correct answer.
But sir, if we take
What is the unit of K you have taken?
m meter square, sir, and the unit of s is meter,
Yeah, so that
and
is what I was explaining in earlier slide. Why we needed the extinction coefficient, because you need to have the unit of the K every time verified, because K can be the centimeter square per gram or centimeter square per molecule, okay, or centimeter square per volume. So what is that unit you have actually had when you started? So in these equations, as I mentioned before, this is centimeter square per gram. What is the rho? So rho is a gram per meter cube or gram per centimeter cube, whatever unit you want to write.
sir, gram per centimeter. Rho is
So let us
gram.
say gram per centimeter cube, and this is centimeter square per gram. Hers has given answer onto the comment box. So meter per gram. Okay, he wanted to say meter square, but probably he has typed it wrong. But yeah, now he has typed correctly. Meter square per kilogram into kilogram per meter cube into meter, and that meter into meter comes from this ds. This ds term in this equation has a unit. Okay, it's not unitless. It is into the terms of the length. Okay, this is a physical length, and it has a unit of meter or kilometer or whatever unit you decided in this equation. Okay, and if you multiply these things, it will be the unit less. Okay, so yeah, so let's so I think let's end here today's lecture. What I wanted to cover more, did I? Okay, in this equation, I have made a mistake here. There should be a negative sign. So if you are watching this recorded things, you should be careful, okay, before using this equation here. Okay, and here also there will be this will be kind of a positive sign. So anyway, so okay, I think we will end here and we will cover all other things next. Thank you. Thank you very much. And anything else you wanted to ask, or if something you missed in between, or you wanted to?
Hello.
Yes.
Sir, in between, sir, you told that there is a relation between refractive index with a scattering coefficient and absorption coefficient. So, sir, can you tell me that again, that one line?
Uh, so I wanted to tell you that what does the scattering cross section and absorption cross section depends on to it. Okay, and that depend on to the refractive index of the material. Okay, and refractive index will have the two parts. Okay, any refractive index, if you ask the refractive index of say water or refractive index of say any material, it will have one real part and one imaginary part. Okay, so real part of the refractive index provides you the scattering properties, and imaginary part of the refractive index provides you the absorption properties. We will cover this. We will do this exercise into the future lectures. But for time being, you remember that why scattering and absorption is different for the different material, because different material has a. So what is that property? Different property of the material, and that is the refractive index. That is what determines the outcome of the scattering cross section and absorption cross section.
So, sir, if one knows absorption cross section, then directly, son, one can calculate scattering coefficient, or one have to measure.
If one knows the refractive index, one can calculate the scattering cross section. So one more quantity that you will require to get the scattering cross section will be the size of the particle. Okay. In case of the absorption cross sections, you really, I mean, it depends on the size of the particle. It's not very sensitive. So yes, you need the scattering. You need the refractive index and the size of the particle to get the scattering coefficient and absorption coefficient of the cross sections. Okay. But for example, CO2 molecules, it has a fixed dimension. It's not like that one CO2 molecule is different from the other CO2 molecules. But when you are doing aerosol, I mean, that particle that we find into the atmosphere, the small dust particles, they will be of the different sizes. So in that case, you also have to take into consideration the size of the particles. But for air molecules, you can theoretically find out what is the size of the molecule, and refractive index anyway you know, then you can do the calculations. So yes, that's all. So if you are dealing with a gas, you will need only the refractive index of the gas. But if you are dealing with the particles, you will also need the size of the particle in addition to the refractive index.
Yes, sir. Thank you, sir.
Any other question? See, I mean, this topic, particularly this subject, is very mathematically intensive. I mean, there are lots and lots of equations, okay? And when earlier I was teaching, I used to have kind of a whiteboard. I mean, I will do the calculations on the board, and then so it is easy to follow that how from one equation to the other equation was derived, okay? Uh, in the online mode, I'm kind of trying to get the hardware that I can actually do kind of a whiteboard kind of things, but I don't know when it will happen. But I would like to have your suggestions that what should I do differently that or that you would like to see. I mean, what is that? Uh, in what way this lecture should be presented so you would be able to follow it properly. You can send these your suggestions onto the email or some. You have my email ID, or otherwise you can send it to the pages and let me know. So maybe I will try to incorporate that.
Sure, sir.
Okay, then if there are no more questions, then I will leave the meeting.
Okay, sir. I think there are no further questions. Thank you, sir.
Okay, goodbye.
Goodbye, sir.